Hey everybody, I thought I would do a pre-recorded video on some of these Stoich problems because I have a feeling that our AP Unit 4 review, which is all about reactions, types of reactions, signs of reactions, calculations involving reactions, which is of course stoichiometry. I think that lecture might run a little bit long for in class, so I thought I would pre-record some of the problems just in case we run out of time. So, and you guys know how much I love Stoich. So let's make a video. Here we go. We obviously know that stoichiometric calculations are the study of the quantitative relationships involved in substances in a reaction. And back in honors chem, that was always just simple, easy dimensional analysis type problems. But of course, now with all the chemistry that you guys know, the world is our oyster, and we can do so many different types of problems involving stoichiometry. So let's start out with just sort of a standard Stoich problem, like a limiting reactant, theoretical yield, percent yield type of problem. But let's incorporate molarity and gas laws and maybe a little bit of thermo too. Wouldn't that be fun? Okay, so our first problem here says that we have a 0.56 gram sample of zinc that reacts with 15 milliliters of 0.3 molar hydrochloric acid. The hydrogen gas produced is collected over water at 25 degrees Celsius. Okay, so let's diagram that all out. Let's write the reaction and go from there. So as I'm doing this, so should you. Okay, let's see. So you guys have done labs where you've collected gases over water. There's a bunch of different setups, but probably the one that you're familiar with is using a eudiometer. And a eudiometer is like a real tall, skinny sort of like test tube, maybe like graduated cylinder type looking thing. Okay, well, it wouldn't be that shape, but you get the idea. And you would fill that eudiometer up with water, and you would plug that eudiometer with a stopper. That stopper would have a hole in it in order for the displaced water to come out. So of course this is going to be inverted in a beaker of water. So this is full of water. Let's see, we've got a sample of zinc down in here. Okay, that was supposed to be green. Try again. Green. Okay, so here's my chunk of zinc. So this is a 0.56 gram chunk of zinc. And we know that as this reaction takes place, and of course there's going to be some HCl in here as well, we know that the hydrogen gas is going to bubble up to the surface. And so that water is going to be displaced out of the eudiometer. So all of that water is going to sort of push its way out of the hole in the stopper. And up here at the top of the eudiometer will be some hydrogen gas. That's the gas that I collect and I care about. Okay, now of course also up in here is going to be some water vapor, because whenever we collect a gas over water, there's going to be some water that turns into the gas phase as well, which is going to contribute to our total pressure inside this container. That'll come into play a little bit later on. Okay, so that's our diagram of our setup. Let's go ahead and write a balanced chemical equation. Nope. That's what happens when you try to balance an equation at the same time as you're writing it. Oh, I hope I haven't gone off screen. Have I gone off screen, you guys? Ooh, just barely. Okay, so there's my balanced chemical equation. Let's do some other things with this balanced chemical equation. So maybe I'll scroll over here to make sure we don't run out of room. Let's say that this reaction has a delta H. Oh, freaking frack. Forgot to look up the delta H of this reaction. Should I just make up a number? Okay, I'm gonna make up a number. I know that this reaction is exothermic. That I do know. The magnitude to which it's exothermic, I have no idea. So I'm just gonna make up a number. Let's just say it's negative 55 kilojoules per mole of reaction. So like as per this balanced chemical equation, let's say that's the delta H, because I wanted to have some fun with that a little bit later on. Okay, so looking at this reaction based on what we discussed earlier today, this reaction is a single replacement reaction, but it's also a redox reaction. Let's go ahead and practice our redox a little bit. Let's assign some oxidation numbers. Elements in their standard states are 0. Do you see why I wanted to record this ahead of time? I'm going to make this video super long, and we're going to review like everything we know about chemistry in this one video. Are you excited? All right, hydrogen is typically a +1, which is going to make my chloride a -1. Here, zinc is a +2 ion, and chloride remains a -1. There's my spectator, and hydrogen element at standard state 0. Okay, I'm starting to see my redox reaction taking place here. My zinc is going from a 0 to a +2. How do we go from a 0 to a positive charge? Through the loss of electrons, and this, of course, we now know is oxidation. And my hydrogen is going from a +1 to a 0 through the gain of electrons, which, of course, we now know is reduction. And by assigning oxidation numbers, we've also identified that chlorine is a spectator ion. We could go ahead and write out a net ionic equation, which is one of the other skills that we should be able to do, where we separate the things that are aqueous only, and we cancel out ions that are the same on both sides. So in this case, that's going to be, I can just sort of see the whole thing in my head, and I can go right to a net ionic. Those chlorides are going to cancel out as spectators. So really, zinc is going to a zinc 2+, and we're producing some hydrogen gas. I just had a terrible feeling that I'm not recording. Am I recording? Oh yes, I'm recording. Oof, that'd be bad. Okay, so there's my net ionic equation. If I was asking you more redox questions, another redox question I could ask you would be like, how many moles of electrons were transferred? Hopefully you could see from the balancing of charges that that was a loss of 2 electrons and a gain of 2 electrons. So 2 moles of electrons being transferred in total. Anyhow, back to the stoichiometry, shall we? In fact, I didn't actually even ask you guys a question yet. Let's say that the question is this. Let's say I want to know how many milliliters of hydrogen gas should be produced if, let's say, the pressure total is equal to 763 torr at 25 degrees Celsius. So in other words, if we're talking about how much should be produced here, you guys, what we're looking for is the theoretical yield. How much product should we be able to make in this reaction? Oh no. I just realized that the stuff that I'm writing down lower, you guys can't see either. I better scroll up. Okay. Oh my gosh. See, this is why I should not make these recordings on my big screen. Ay, 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 Amanda. Okay. Here's the question. How many milliliters of hydrogen gas should be produced if the total pressure is 763 torr at 25 degrees Celsius. Now, to figure out the theoretical yield, what we need to do are two sets of dimensional analysis, working from grams of zinc to how much product we should make versus milliliters of hydrochloric acid, because we don't know what our limiting reactant is yet. So we need to do, there's lots of different ways to find a limiting reactant. You guys know this, but I like to do it by going two sets of dimensional analysis, figure out which one makes the least amount of product. So that's what I'm going to do. Okay, here we go. I'm going to scroll up. I have to double check all my screens, make sure you can still see. All right, and we're going to do two sets of dimensional analysis. Starting off, I'm going to start with the zinc. Okay, so I'm going to start with my, I'm going to start with my 0.56 grams of zinc. I know that 1 mole of zinc has a molar mass of something, like 63 or 65. I'll look that up in a minute. Off of my balanced chemical equation, I know that 1 mole of zinc will produce 1 mole of hydrogen gas. I'm actually going to go ahead and stop there because I'm going to have to use PivNert once I know how many moles of gas I can produce, and I don't feel like doing PivNert twice. So what is my molar mass of zinc? So you guys, this is why I ordered that periodic table for my office, but it's too big. So now I'm stuck looking up stuff on my phone. 65.4. Okay, so 0.56 times 1 times 1 times 1. Okay, so divided by 65.4. Okay, my zinc would be able to produce 0.00856. moles of H2 if all of my zinc got used up. Now let's work with the hydrochloric acid. How much hydrochloric acid did I say we had here? Okay, 15 mils of 0.3 molar. Okay, 15 mils of 0.3 molar. 15 milliliters of HCl. 0.3 moles of HCl per 1,000 milliliters. Go ahead and use my molarity as a conversion factor. Balanced chemical equation tells me I need 2 moles of HCl for every 1 mole of H2 produced. So 15 times 0.3 divided by 2,000. 0.00225 moles of H2. So I look at these two values, and whichever one of these values is smaller is how much H2 I should be able to make. In other words, my HCl is my limiting reactant because it can only produce 0.00225 moles of H2. Okay, so my HCl is my limiting reactant. Now, this right here is my theoretical yield of hydrogen gas, but that's a theoretical yield in moles. And my question is asking for my theoretical yield in milliliters. And of course, I need to use PivNert in order to figure out what that volume is going to be if I'm not at standard temperature and pressure. So here's the other tricky thing here, is we collected this gas over water. And I'm being told that the pressure total is 763 torr at 25 degrees Celsius. But don't forget that we also have water up there in that eudiometer. So we needed to subtract out the water vapor pressure in order to get the pressure of just the dry hydrogen gas. So let's do that. Now that would be a standard value that we would have to look up. And if I looked up the water vapor pressure at 25 degrees Celsius, the pressure of the water vapor at that temperature, I would find it to be 23 23.8 torr. So if that's 23.8 torr and my pressure total is 763 torr, that means that the pressure of my dry hydrogen gas is simply those two things subtracted from one another. So 763 minus my 23.8 gives me a pressure of 739.2 torr. So now I can use Pivnert, right, you guys? Let's Pivnert it out. What am I looking for? PV equals nRT. All right, so I'm looking for volume. So volume is going to be equal to nRT over P. My moles of gas is my theoretical yield, 0.00225. My 0.0821 is my constant. My temperature is 298 Kelvin. And okay, hopefully you can't hear Parker. He's being pretty silly. And my pressure of my dry hydrogen gas, I got to turn my 739 torr into atmospheres by dividing by 760. So my pressure in atmospheres is 0.973. All right, let's knock out this calculation real quick. Times 0.0821 times 298 divided by 0.973. And this is liters, got to change it to milliliters, so I'm going to multiply by 1,000. All right, I get 56.6 milliliters of hydrogen gas produced. That right there is my theoretical yield. That's how much hydrogen gas I should be able to make in this reaction. What if the problem also asked, I'm just going to keep adding stuff to this problem. What if the problem said, you know what, actually in the lab, you only made, what if your actual yield in the lab was only 50 milliliters of hydrogen gas? If that's what you actually got in the lab, what is your percent yield? And of course we want our percent yields to be nice and high. Okay, yield has a L in it. Percent yield is your actual yield, your 50 milliliters, over your theoretical, how much you should have been able to make if everything went beautifully in the lab, times 100. So the percent yield for this reaction, if I gave you that actual yield of 50 milliliters, or if that's what we actually got in the lab, 50 divided by the 56.6 times 100 would be like an 88.3% yield, which is pretty good. Honestly, once you guys go to Orgo Lab and you try to start synthesizing things, you're going to be really shocked at how little you get compared to how much you wanted to get or expected to get out of your reaction. Okay, what else did I want to do with this problem? Oh, okay, I remember. Let's say, we could have like lots of fun with this. Let's say that all of the HCl reacted, right? So our hydrochloric acid was our limiting reactant. And so let's say that all 15 mils of that 0.3 molar reacted. Okay, so like this right here was our limiting reactant. What if I asked you the question, if all of that reacted, how much heat would you make, would be produced? I know I'm probably going off screen. I'll scroll here in a second, you guys. Sorry. Okay, so in order to solve this problem, now we have to pay attention to the fact that we have a delta H of our reaction. And so to solve this problem, go back to my green, Let's just do a little bit of simple Stoich again with our limiting reactant. We know that there's 15 milliliters of it. We know that it's 0.3 molar. And we know that based on the moles of this balanced chemical equation, we're going to get negative 55 kilojoules. We don't get negative heat, but you know what I mean. The heat is going to be released. This many kilojoules of heat are going to be produced for every 2 moles of HCl, because that's what it means to be per moles of my reaction, is per what is given in my balanced chemical equation. And so I know that this reaction, because the HCl is limiting, I am going to get now in kilojoules, it's kind of a small number, so I'm going to go ahead and change it into joules. I'm going to get 123.7 or 0.8 joules of heat released. I could even go farther, you guys, and ask like what the change in temperature of the water would be. Ooh, wouldn't that be fun? Oh my gosh, are you guys getting annoyed? Do I have enough room? What if, like, let's go back to this diagram here. Like, let's say that this was like 200 grams of water total in this system. And let's, say energy is conserved. This is all really well insulated or whatever. And let's say that this water, of course, started off at that 25 degrees Celsius that we were talking about. What is going to be the change in temperature? Like, what's going to be the final temperature of that water? Ooh, fun, fun, fun. Let's bring in some thermo. Okay. This is impossible because I have like so much more screen that I'm seeing than you guys are seeing. I'm going to have to like squish this in really tiny over here. All right, so if I'm getting this much heat released by my reaction, that's how much heat is being absorbed by my water. So a positive 123.8. What are we talking about here? Joules. So that's my positive. So here's the equation I'm working with, you guys. Q equals mc delta T. So this is how much heat is being absorbed by the water that's being released by the reaction. So if the water's absorbing this much heat, and we've got like 200 grams of water, and the specific heat of water is 4.18 joules per gram degrees Celsius, what's my delta T gonna be? You guys know so much chemistry. So much, so much, so much. 123. Ooh, that's bad on my calculator. 123.8 divided by, are you guys doing these along with me? I hope so. If you're just watching it, you're probably falling asleep. 0.148 degrees Celsius. So my water that was at 25 degrees Celsius is going to rise up to 25.148 degrees Celsius. Now that's not a huge delta T, but I wasn't talking about a huge amount of heat anyway, right? We're talking about joules, not kilojoules, and water has a pretty high specific heat, meaning it takes a lot of heat to change water's temperature by 1 degree Celsius. Okay. Goodness gracious, that was a big old problem. Is there anything else I wanted to do with it? I don't think so. Should we do another? Yes. Let's do another problem. Okay, gravimetric analysis. Gravimetric analysis is a tool that we use in the lab to use mass measurements to identify compounds or to identify percent compositions of mixtures. So there's two different types of problems that I would like to do with you guys. Nope, never mind. There's two different types of combustion analysis problems I want to do. There's only one type of gravimetric analysis I want to do. Okay, so let's do it. Let's say I have a 4.33 gram sample of a alkali metal hydroxide. Okay, so we're talking alkali metal hydroxide. That's talking about a group 1 metal. It's always a good habit to write down what I know. Group 1 metal hydroxide is completely dissolved in water because I know that my alkali metals are super duper soluble. And so let's just start drawing ourselves a diagram, shall we? So like here's my beaker and here's my water. 4.33 grams of some unknown metal hydroxide. Okay, so this is going to go in here, and I'm obviously going to end up with a bunch of M1 plus and OH1 minus ions floating around. Okay, then the problem says that I titrate this sample. So I'm going to, add using a burette. Okay, my scale is pretty terrible here. I'm going to titrate this sample with copper 2 nitrate in order to precipitate out copper 2 hydroxide. Okay, so I'm basically going to add to this some copper nitrate. So maybe I should just start writing the reaction. Maybe that'll help. MOH plus CuNO3 2. All right, so this looks like a double replacement reaction where I'm going to get some CuOH2. That's the precipitate they were talking about. And whatever that, metal nitrate is, 1 plus 1 minus, because I know it's an alkali metal. That's going to be soluble. Okay, so there's my reaction. All right, so I'm going to titrate this, and in the end, the problem told me that I precipitated out. Okay, so out comes my precipitate. The precipitate is my CuOH2 solid, and the problem says that I precipitate out 3.81 grams of this stuff. All right, I didn't balance my reaction, you guys, sorry. Probably should have done that. So I've got 2 nitrates here, 2 nitrates there, 2 right there. And yeah, I'm good. Okay. So now the question is asking, what's the metal? Like, what is the metal hydroxide? Now, there's a couple of different ways you could go about that. Like, you could figure out what the molar mass of this metal hydroxide is. You could figure out percent composition of the metal hydroxide. Either way would work. So if you want to go ahead and pause this and solve it your way, go ahead. I'm going to go ahead and solve it with percent composition first. And then we can go back if you haven't totally checked out yet, and we can do it by molar mass. Okay, so here's how I'm going to do that. I'm going to work from my 3.81 grams of my product. Okay, so if I know that I have 3.81 grams of copper hydroxide, I can figure out how much of that is just hydroxide. Because if we think about it, all of the hydroxide that we get in that precipitate came from my initial compound. That's where it actually came from. It came from here in solution. So if I can figure out how much hydroxide I have in that precipitate, that's how much hydroxide I had in this initial sample. And so then I can get percent composition from that. Okay, so let's go ahead and do that. So I need the molar mass of copper hydroxide, OH2. Okay, molar mass of copper hydroxide is 98 grams. That one I wrote down ahead of time. Aren't you proud of me? And for every 1 mole of copper hydroxide, I get 2 moles of hydroxide. And for every 1 mole of hydroxide, I have a molar mass of 17 grams. This calculation right here will give me the mass of hydroxide that was in my original sample. 3.81 times 2 times 17 divided by 98, 1.32 grams of hydroxide. So if my original sample contained 1.32 grams of hydroxide out of a total mass of 4.33 grams of MOH, that gives me a percent composition divided by 0.3, nope, times 100. So 30.5%. So now I can go back to the original problem and I can figure out the percent compositions of the different alkali metals that I was asked to compare to. So like the question was asking, is this lithium hydroxide, sodium hydroxide, or potassium hydroxide? So if my metal sample, oh, why am I getting these weird dots? Erase those. Okay, so what am I trying to figure out? Lithium hydroxide, sodium hydroxide, or potassium hydroxide? Just go through here, you guys, and figure out the percentage of hydroxide in each of these samples, just based on molar mass. So like lithium hydroxide would be, that's not right. Oh, I see what they were doing. Just kidding. I was looking at an example problem and it like did not seem right at all. Okay, so compare this 30.5% hydroxide to the percentage of hydroxide in each of these. And so like if we were to look at lithium hydroxide, the percent of hydroxide would be similar mass of the hydroxide, 17 grams over the total, 17 plus 7 over 24 grams times 100. Oh my gosh, am I working off screen again? Yes. Better. Okay, so 17 divided by 24 times 100. So the percentage of hydroxide in lithium hydroxide is 70.8%. Okay, so it's not lithium hydroxide. Let's figure it out for sodium hydroxide. So 17 grams over, what would my total be? So 17 plus 23 over the 40 grams. So my percent of hydroxide in sodium hydroxide is 43%. Oh, of course it's going to be the last one. All right, so it's not, oh, sorry, I didn't label this one. It's not sodium hydroxide. So let's double check and make sure that it is in fact potassium hydroxide, which would be a molar mass of 40 for potassium. No, I'm trying to do hydroxides percent. 17 grams over the 57 grams times 100. Hopefully this is our winner. And it is. Yay. This is 30% hydroxide, which matches with the percentage of hydroxide that I found up above from my experimental gravimetric analysis. Okay, so I don't feel like doing that problem again, do you? I mean, we could figure out how many moles of hydroxide. In fact, maybe that would have been the easier way to do it. Figure out how many moles of hydroxide. We could have just stopped up here in this dimensional analysis. If we stopped up here at moles of hydroxide and divided my, what was it? 4.33. Oh, no. It wouldn't have been moles of hydroxide. Sorry. Moles of compound. Would have been moles of total compound. If we stopped and figured out moles, wait, could I have even done this problem this way? Okay, you guys, sorry about that. Let me let me restate how we would solve this problem by solving for molar mass. Maybe I'll just like switch colors so I stop confusing myself. Okay, if we wanted to solve for this by solving for the molar mass of the unknown compound, I would have gone from the 3.81 grams of the copper hydroxide. I would have converted that into moles, just like I did up above with that molar mass of the copper hydroxide. And then for every 1 mole of copper hydroxide that I precipitated out, I know that that would have required 2 moles of that unknown metal hydroxide. This here would have given me the moles of my initial sample. So 3.81 times 2 divided by 98 is equal to 0.0778 moles. And if I know that originally I had 4.33 grams, and I divide that by the 0.0778 moles, this gives me the molar mass of that unknown compound. Gives me a molar mass of around 56 grams per mole. And then I could have compared that to the molar mass of the lithium hydroxide, the sodium hydroxide, and the potassium hydroxide. And of course, we know that it's potassium hydroxide. And if we go back and take a look at the molar mass of potassium hydroxide, it's very close to that 56 grams per mole that we got. So we know that we could also figure out the identity of the unknown substance simply by calculating molar mass. In fact, I think that's a much more elegant way of doing it, although I would have had to go through and calculate the molar mass of each of those things as well. So anyway, 2 different ways to go about doing that. Okay, let's do a titration problem. Concentration of an unknown through titration. Let's draw it out. All right, so let's say we have a 20 milliliter sample of the base potassium hydroxide, and we are going to titrate that with a titrant of, oh, I didn't give you a molarity. Jeez Louise. Okay, 23 milliliters of, let's say, you needed a molarity in this problem, you guys. Let's say the molarity was 0.35 molar sulfuric acid. Okay, so 0.35 molar H2SO4. And let's say that it required 23 milliliters of this acid in order to reach the equivalence point. Now, how will you know that you've reached the equivalence point? Like if we were thinking about actually setting this up in the lab as a method for determining the concentration of the KOH, we would have needed to have picked an indicator to change color so that we know when we reached the equivalence point. Or we could have used a pH probe, a pH meter, and looked at the pH curve. In fact, this pH curve would have started off basic, and we would have known that our equivalence point is at the middle of that steep rise, or in this case, fall in the curve. So that if this is our pH and this is volume of acid added, at this point is where we have reached our equivalence point. So either we used a pH meter to get there. For a strong acid, strong base titration, this pH at the equivalence point should be pretty close to 7 because there's not going to be any salt hydrolysis happening. I would love to spend more time talking about this, but it's not going to be on the AP exam this year because of Corona. Okay, so we would have wanted to have picked an indicator that changed color at around a pH of 7. We probably would have used phenolphthalein, which changes around pretty close to 8. So in the 7 to 8 range would be good enough for this titration. All right, so obviously we want to use a balanced chemical equation in order to do our stoichiometry. So I'm going to scroll, make sure I don't run off screen here. All right, so KOH, here's my base, plus my H2SO4, which is my acid. Acid plus base, double replacement, neutralization reaction, makes salt and water. No, it's not sodium, it's potassium. Alkali metals are always soluble, and liquid water. I'm gonna balance this guy. Okay. We could also do a net ionic equation, and if I was doing a net ionic equation for this reaction, this being a strong acid and a strong base, my net ionic equation would be 2OH minus plus 2H plus, making 2H2O, which would of course reduce a 1-to-1-to-1 ratio, where our moles of acid are neutralizing our moles of base to make water. Anyway, that was just a little extra review on net ionic equations. Let's go ahead and do our stoichiometry. We want to know the molarity of this base, and we titrated 20 milliliters of it. It required 23 milliliters of this acid, which was 0.35 molar, in order to do so. Now, some of you, aka Justin, like to use cheat methods to solve these kinds of stoichiometric problems. I, however, love dimensional analysis, and that is what I'm going to use. So here we go. Start with the thing you have the most information about, which would be the acid. So we know that we have 23 milliliters of H2SO4. I know the molarity of it. Just going to put it over 1,000 mils. Mole ratio between my acid and my base. Oh my gosh, people are banging around upstairs. 1 mole H2SO4 for every 2 moles of KOH. I hope some of you guys live in old colonials so that you feel my pain when you hear people like banging around upstairs. Sounds like they're going to come right through the ceiling. And okay, I'm going to stop here at moles of KOH. So all I'm doing here is I'm going from volume of acid to molarity of acid to moles of base that were neutralized by that acid. So if I know how much base was in that aliquot or that sample, I can calculate its molarity. So let's first get the moles of it. 23 times 0.35 times 2. Divided by 1,000, 0.0161. Oh my God, that scared me so bad. I made a goofy thing on my M. Woof. Maybe I should have my house checked by an architect. This is how many moles of potassium hydroxide we neutralized. And if we want to know the molarity, now all we have to do is divide by the liters that were neutralized, 0.020 liters, which gives me a molarity of 0.81 molar KOH. Voila. We have calculated the molarity of an unknown species. One thing I would like to highlight for you here with this titration, you guys, is the mole ratio. And the reason why this is a 1-to-2 mole ratio, why we need twice as many moles of base in order to neutralize the acid, is because this is a diprotic acid. So don't forget about your, the number of hydrogens and the number of hydroxides in your species matters. And it matters in terms of how much base you're going to need in order to neutralize those 2 hydrogens in the sulfuric acid. Okay. The dumb cheat method that you guys would want to use would be the dilution equation thing. I guess I'll go ahead and show it to you. I don't know why. I'm caving to your demands. Molarity of the acid, volume of the acid, molarity of the base, volume of the base. You're taking this dumb cheap method from the dilution equation, M1V1 equals M2V2. But what it fails to account for, you guys, is this mole ratio, this 1:2 mole ratio. So if you want to do this cheap method, on the side of the acids, you have to put the number of hydrogens that are in the acid, and on the side of the base, you need to put the number of hydroxides that are in the base. Okay, so to do this problem, you would have to put a 2 over here times the molarity of the acid times the volume of the acid. See, this just doesn't show any understanding. Molarity of the base, volume of the base, and how many hydroxides were in the base? 1. Okay, so like, yes, this will work to give you the molarity of the base. Okay, but I just don't think it's as science-y a method. I'm not even going to calculate it for you. So there you go. Okay. Woo, we're cranking along, cranking along, cranking along. All right, we've done a bunch of Stoich. Let's do just a little bit more. All right, combustion analysis problems. Combustion analysis problems are problems that take a look at how much stuff gets produced when you burn things, right? So like technically a combustion reaction is any reaction with oxygen. Now, there's a couple of different types of combustion. Obviously, there's your traditional combustion, which is like a combustion of a hydrocarbon. That hydrocarbon sometimes contains oxygen, sometimes it doesn't. But regardless, these combustion reactions always produce carbon dioxide and water if they undergo what we call complete combustion. Incomplete combustion can result in the production of some carbon monoxide as well, which is why why burning fuel in our cars is not so great, because besides producing carbon dioxide, it also produces carbon monoxide. But technically, even like the reaction of iron with oxygen in the air to produce rust, this reaction technically is also a combustion reaction. So don't get too tied up in combustion only ever producing CO2 and H2O, but that's your sort of traditional hydrocarbon combustion. Okay, so we can burn things to figure out what they are, and that's called combustion analysis. And so let's take a look at this first problem. This first problem says that a compound containing hydrogen, oxygen, and carbon is burned. And in burning it, produces 44 grams of CO2 and 27 grams of H2O. What is its empirical formula? Now, I apologize. I can't get subscripts in this thing. I think I told you before I was going to figure out how to do it, and then I never did. Anywho, here are possible empirical formulas for this compound. CH4O, I'm just going to go ahead and write them with subscripts because this is bothering me. CH4O, C2H6O, C2H3O2, and C3H5O2. So what I basically need to figure out, based on this information that I'm given, this 44 grams of CO2 and 27 grams of water, I need to figure out like what are my proportions of carbon to hydrogen in these products. So I know that if I've got 44 grams of carbon dioxide, 1 mole of CO2 is 44 grams. And for every 1 mole of CO2, I get 1 mole of carbon. So basically this means that, this substance essentially started off with 1 mole of carbon in it, right? Because I got 44 grams of CO2, and the only place I get the CO2 from is from the original hydrocarbon in the original carbon in the hydrocarbon. Like that's where all of the carbon from the CO2 comes from. The other thing I can work with is my 27 grams of water. And I know that the molar mass of water is 18 grams. And for every 1 mole of water, I get 2 moles of hydrogen. So 27 times 2 divided by 18 is 3. Now, I didn't bother with the oxygen in this case, you guys, because the oxygen in the carbon dioxide and in the water not only could have come from the carbon-based compound that we were starting with, but also the oxygen it reacted with in the air. So what's nice about working with the CO2 is you can get just the carbon from it. And what's nice about working with the hydrogen is you can get just the hydrogen from it. Because the hydrogen from the water and the carbon from the CO2, they both came only from this initial compound. They did not come from the oxygen in the air. So let's just ignore the oxygen in the air. And let's try to find an empirical formula that has a 1 mole of carbon to 3 moles of hydrogen proportion. So 1 mole of carbon for every 3 moles of hydrogen. And the only empirical formula that has that 1:3 ratio is the C2H6O. Like I didn't even have to worry about the oxygen. And in fact, I didn't have enough information to figure out how much oxygen was in that initial compound. That will be a different type of problem that we will look at next. So let's do so. This will be our last problem for today. Hooray. This has been a long lecture. Hopefully we get through a lot of this in class tomorrow. Okay, so let's say I have a different type of combustion analysis problem. Let's say that this problem tells me that a 0.105 gram sample of a compound is burned. And again, I'm given a mass of carbon dioxide and a mass of water. But the key piece of information that I'm given in this problem that I was not given earlier is I was given the mass of the original sample. And this mass of the original sample is going to allow me to figure out how much oxygen I had initially as well. But I'm getting ahead of myself. So let's start off with the 0.257 grams of CO2. And let's figure out how much carbon is really in this compound. So 1 mole of CO2 has a molar mass of 44 grams. For every 1 mole of CO2, I get 1 mole of carbon. And for every 1 mole of carbon, I've got 12 grams. I'm going to do this same process here for the water. Let's figure out how much hydrogen is in that water. 0.350 grams of water. Make sure you guys can see what I'm doing here. You can. 1 mole of water, molar mass of 18 grams. Getting lazy with my labels. For every 1 mole of water, I get 2 moles of hydrogen. For every 1 mole of hydrogen, 1 gram. Okay, let's go ahead and calculate these out. So 0.257 times 12 divided by 44. Okay, so I've got 0.0701 grams of carbon. Doing my hydrogen calculation now. I've got 0.0039 grams of hydrogen. Okay, so once I have grams of my carbon and my hydrogen, if I know that my original sample contained 0.015 grams total, all I have to do is subtract out my carbon mass and my hydrogen mass to get the mass of the oxygen. So 0.105 minus 0.0701. My mass of oxygen will be 0.03 0.31 grams of oxygen. So now I can, ooh, I was almost out of space there, you guys. Sorry about that. Now what I can do is a standard empirical formula problem where I go from mass of carbon, mass of hydrogen, and mass of oxygen to figure out the empirical formula of the compound. Okay, so I'm going to use these three mass values, convert them all to moles, divide by the smallest to get a mole ratio, blah, 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 blah. All right, here we go. 0.0701 grams of carbon, 1 mole, 12 grams. And 0.0039 grams of hydrogen, 1 mole, 1 gram. And 0.031 grams of oxygen, 1 mole, 16 grams. Okay. And let's calculate these out. 0.0701 divided by 12. Don't round too early here because we don't want icky mole numbers. 0.0039 0.00194. All right, I'm going to divide by my smallest. And hope we get good numbers. Obviously, this one is 1 divided by 0.00. Beautiful. 2 hydrogens. Voila. C3H2O. My empirical formula. Now, this is not the only thing that the problem was asking me for. The problem was also asking for a molecular formula. And we know that the molecular formula is some whole number times the empirical formula. And we get that whole number by dividing the mass of the molecular formula by the mass of the empirical formula. You know, this mass of the molecular formula being the true molar mass of the compound, which we could get through, you know, like boiling point elevation experiment or freezing point depression experiment. There are ways of figuring out the molar mass of an unknown. And so we were given that molar mass of the unknown way back up here at the beginning of the problem. It said that the molar mass of the compound was 108 grams per mole. Okay, back down here, 108 grams per mole divided by whatever the empirical formula mass is. Let's figure that out. Plus 54 grams per mole. That looks like a 2, which means my molecular formula of this compound is C6H4O2. Take that coefficient, multiply it through by 2, and the combustion analysis has given us both an empirical and a molecular formula. Good job, you guys. That was a lot. I hope you had as much fun doing stoichiometry as I did. Good luck on the AP test.